Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Step 1 inside as we hit section 9.6 on solving right triangles in the Big Ideas Math Integrated Math 2 textbook, where it includes everything right triangles in trigonometry. And this section, I don't know for sure on how they ask the questions. There's probably not as many as you'd like, but this section almost counts as a review for the entire chapter itself, I feel, because solving right triangles means find all missing sides and all missing angles within them. That means we could use Pythagorean theorem if we wanted to. We're probably going to use more trig. We use trig if we wanted to, and we're going to learn things likely to solve missing angles using inverse trig, and we'll probably do the special right triangles 30, 60, 90, 45, 45, 90, maybe a Pythagorean triple here and there. Case in point, this really is a way to kind of review everything. If it says find a missing part, we have different ways to do it. I'll try and follow the book as often as I feel that I need to with this stuff, and it's probably going to more heavily emphasize trig. So it's probably going to be more about sections 9.4 and 9.5 when we learn about sine, cosine, and tangent. And they won't use the phrase, but I started using it in 9.5, SOHCAHTOA. So if you remember SOHCAHTOA, that will help you out a lot. If you'd like to follow along, download the PDF down below, where I start the lecture portion right now, or momentarily, and after that we go to the problem set of, I think, less than 30 problems. I can't actually remember. I started creating the thing last night, and I haven't yet seen the problems. But let's go ahead and take a look. Get your calculator ready, by the way. If there's something that you learned in trig, it's that we got to use the calculator. So what will you learn? We will learn to use inverse trig ratios. Yes, this will be used to find missing angle measures. I'll talk about it more if they don't, as far as exploring why that is and what it looks like. And solve right triangles, which I said means find every missing part of your triangle. All three angles, all three sides. Obviously, one of the angles is 90 degrees, so that's not one you need to find. Using inverse trig ratios. Oh, sorry, before that. Inverse tangent, inverse sine, inverse cosine, solve a right triangle, new core vocabulary. Note the way that they do say this and the syntax that will be in play. Please make sure that you say these phrases, not what they'll show you. You'll see what I mean in a second. Using inverse trig ratios, identifying angles from trig ratios. Determine which of the two angles has a cosine of 0.5. So let's see how they talk about it. They say the cosine is adjacent to angle A over hypotenuse, which is 0.8660. And cosine of B is 1 over 2, being adjacent over hypotenuse of B, and that's 1/2, so it's 0.5. Therefore, the acute angle that has a cosine of 0.5 is angle B. Is this actually an example? If the measure of an acute angle is 60 degrees, then its cosine is 0.5. The converse is also true. If the cosine of an acute angle is 0.5, then its measure is 60 degrees. So in example 1, measure of angle B must be 60 because cosine is 0.5. So if they have us do examples like that, I guess we kind of have to play a guess and check with it. I'm going to... I was doing this a little bit in the last section, and I kind of stated the obviousness of which one it would be, because they said 1/2 at the time, so I was like, all right, well, it's the one that would reduce to 1/2. So I don't know. We'll see what they look like on the problems themselves. That wasn't actually using inverse trig yet, by the way. That was understanding that a 60-degree angle always has a ratio of 1/2 and vice versa. Okay, so here we go. Here's the actual portion on inverse trig. Let A be an acute angle in a right triangle, right here. An acute angle in general. The inverse tangent and sine and cosine are used like this. If you take the tangent of an angle and you get a ratio, right? This is an angle and this is a ratio. Remember, it's some sort of opposite over adjacent or opposite over hypotenuse or adjacent over hypotenuse. Then the inverse tangent of the ratio equals the measure of the angle. So this is the ratio and this is the angle. What are they actually showing? I think I'll deliver more on this when I do my own problems to say literally what's going on there. But this is the syntax for inverse tangent. The expression, as people would say, tan negative 1x, or whatever, is read as the inverse tangent of x. This is the syntax used for it. If you recall, we've used that syntax for function of x and inverse of your function of x. It has that to the negative first power appearance. It does not literally mean to the negative first power. It is just the notation that is used. It's the same notation your calculator likely uses. There's another one that they can use called arctangent. I don't believe that they are using that here. At least this one can be fully differentiated between that and, say, tangent to the negative first power. So the inverse tangent of something is the same way as any other inverse works. The inverse of multiplication is division, but they call it division instead of inverse multiplication. The inverse of addition is subtraction, but they call it subtraction instead of inverse addition. The inverse of squaring something is square rooting something, right? So tangent, sine, cosine, and tangent trig functions also have inverse trig functions to get something by itself. What's the point of this? If you know a ratio, we can take its inverse sine, cosine, or tangent to get the measure of said angle. If I know the ratio of opposite over adjacent, let's say this x over y, and I can take the inverse tangent of that x over y, you know what I'm going to get? This angle itself. Now, I teased at this or hinted, actually, full disclosure, I think there's a problem I did. It was number 57 or something like that in my last thing where I actually showed how you do this, even in the calculator, but I'll show you it here again as well. So anyway, you take the sine, cosine, and tangent of an angle to get a ratio. You take the inverse sine, inverse cosine, or inverse tangent of a ratio to get an angle. And make sure your calculator is listed in degrees. That way the value that you get is a degree angle measure. So this is true for sine or cosine. Just make sure it's for opposite over hypotenuse for sine and adjacent over hypotenuse for cosine. Let's take a look at some examples in case you were completely lost there. Finding angle measures. Let's let angle A, B, and C be acute angles. Use a calculator. So it doesn't matter if we see it in a right triangle or not. They just said, use the calculator, make this work. So let me kind of write out a little more than what they have here. They have it fine. But if on part A you have tangent of angle A is 0.75, remember what 0.75 represents. It is a ratio of some opposite side divided by its adjacent. This could be a right triangle if this was angle A with side lengths 3 and 4. Clearly this would be a 3, 4, 5 triangle. But tangent of this angle would be opposite over adjacent, 3 over 4, which is 0.5. So what they're saying is you can find the measure of angle A by taking the inverse tangent of both sides. Take the inverse tangent of this side, the inverse tangent of this side. And like all other inverses, do you know what the inverse tangent of the tangent of something is? Those cancel out and you're just left with that something. You're now left with A is the inverse tangent of 0.75. The angle that you have to take the tangent of to get 3/4, 0.75 to begin with. And what is it? Let your calculator do it, but they're going to tell you right here, it's about 36.9 degrees. It's about 37 degrees. A 37 degree angle here, if I took the tangent of it, I would get 3/4. Rounded, of course. I would get 3/4 as my ratio. And that's what we're doing. We're finding angle measures based off the ratios that we know. The sine of an angle, 0.87. This is clearer than that for 3/5 right here, but some opposite over hypotenuse, maybe at 87 over 100. Write a triangle with that. If I get 0.87, what angle measure is that? Take the inverse sine of both sides. See, inverse sine of 0.87, you get 60.5 degrees. Looks like we're going to round to the nearest tenth. Yep, nearest tenth. And then cosine of an angle is 0.15. Take the inverse cosine of both sides. You get 81.4 degrees. And we might start talking about whether or not these answers make sense to us, in what kind of triangle it will be, what the sizes of those legs and hypotenuses are in comparison to one another. And I'm going to do a little more of this probably to begin with on problems, just to get the understanding of how something gets by itself, why it cancels, that kind of thing. We'll probably start more with that before we move further into it when we start to actually solve right triangles, which is going to be next year. Solving right triangles. To solve a right triangle means to find all unknown side lengths and angle measures. You can solve a right triangle when you know either of the following. Two side lengths, in a right triangle, by the way. Two side lengths or one side length in the measure of one acute angle. Reason for this is you can always find a third side using Pythagorean theorem, and you can always find a second angle measure, or a third angle measure, by knowing it's the complement of the other acute angle. So outside of anything else, we can use trig to find the rest of them. So we can use anything we want. I'm going to do my best to leave exact answers in when I calculate as often as possible. If they round early, I'll call it out, but I'm going to try and avoid doing that. To solve a right triangle means to find... Oh, did I already say that? Yes. Solving a right triangle example. Solve the right triangle, round decimal answers to the nearest tenth. So to find the measure of angle... the measure of the hypotenuse, side length C here, you probably just want to use Pythagorean theorem. 2 squared plus 3 squared is c squared, right? That kind of thing. C is going to be the square root of 13. It's about 3.6. Now, I say about 3.6 because it is a rounded value. We still have to find angles B and A. I would caution you on using 3.6 to find measure of angle B or A. So I would avoid using sine or cosine because I don't want to use hypotenuse. Reason being, I don't want to use rounded values. There's a difference between using 3.6 and the square root of 13, for example. If you want to use root 13, go ahead. That's not too bad of a number. It's a problem when you start talking about 13 times the sine of 28 degrees, and that's going to take a lot more to do. So how can I find measures of angles B and A? Well, let's find measure of angle B first, how they do. They're going to use inverse tangent. So measure of angle B is, the tangent of angle B is 2 over 3, opposite over adjacent. The inverse tangent of 2/3 will give me the measure of angle B, which is around 33.7 degrees. Now, I could have used, like I said, inverse sine of, say, 2 over the square root of 13, or inverse cosine of 3 over the square root of 13, but I wouldn't want to use the 3.6 as it's rounded. It might slightly change my answer. Let me show you what it actually would look like on here if I took the inverse sine of 2 over 3.6 versus 2 over 13. Whoops, I'm in radians. I need to be in degrees. You see that? Make sure you are in them degrees. Let's quit out. Let's do that again. Inverse sine of that. 33. Okay, it still gave me 33.7, but you can see how close it was being to round to 33.8 versus if I did the square root of 13 here. All I'm saying is there can be rounding error, and you don't want to count for it. I like to make my points a little bit more stated, but you can see the difference in the answers. And this is the exact, that's an approximated. Don't use rounded answers. Don't calculate with rounded values, I should say. So, how do I find A? Don't spend time using inverse tangent again. Use the fastest way possible. Do 90 minus 33.7, and you'll get 56.3 degrees. Now you'll say, wait a minute, Mr. Robinson, you just said don't calculate with rounded values. I can add or subtract with a rounded value, with one rounded value, because the rounding will stay the same. This 0.7 will stay as 0.7 regardless, because this is exact, and this is just addition or subtraction. If it was multiplication, or a trig function, or a squaring, if it was multiple rounded values, I would not use the rounded values. I would use exact ones. But a single rounded value off addition or subtraction is going to give you the exact same rounding, so that one is fine. Okay, so that is solving the rest of the triangle, finding every part about it. There are two others of which, of course, we're going to do our own thing. Here's another solving a right triangle, but this time we only know one of the acute angles and one of the side lengths, this time the hypotenuse. So I couldn't use Pythagorean theorem to find either of these ones here. Instead, let's use trig to find these side lengths. And we've done this before. This isn't new. Only we have to find both of them. If I want to find h, ignore g for a second. If I want to find h, I can use opposite over hypotenuse. I can use sine. The sine of 25 is h over 13, and you multiply both sides by 13 to get 13 times sine of 25, which is 5.5. So this 5.5 goes here. Could I use Pythagorean theorem now to find g? Yes, but 5.5 is a rounded value, so I'd rather not use that. Instead, go with exact values only, which means I also wouldn't want to use inverse tangent. Let's use inverse not inverse tangent. Instead, I'd want to use cosine. Cosine of 25 is g over 13. Multiply both sides by 13, you get 13 times cosine of 25, which is 11.8. And it makes sense that's the bigger value because of reasons. Now, we still have to find this other angle measure. You have to solve the entire triangle. This will be 65 degrees because it's 90 minus 25. If you wanted to solve that first, then you have a lot of outlets in how you can find this. You can use sine of 65 to find g. You can take cosine of 65 to find h. A lot of outlets, but we have solved the triangle. Okay, solving a real life problem. Your school is building a raked stage. I have no idea what that is. The stage will be 30 feet long. Stage front, stage back. Okay? The stage will be 30 feet long from front to back with a total rise of 2 feet. As long as we have a drawing, that can help us. You want the rake to be 5 degrees or less for safety. Is the rake stage within your... I don't know what... Oh, a rake stage slants upward from front to back to give the audience a better... Oh... I don't know if that actually exists or not. I mean, it exists. I don't know if when I've watched a play or something that actually has ever been the case. I don't feel it has. It makes sense, but better yet, why don't they raise the floor of the audience? Anyway, I guess for the front row people. Okay. Is the rake stage within your desired range? We want it to be less 5 degrees or less for safety, right? It can't be a complete 45 degree incline here. So we're trying to solve for x. I don't know what this has to do. Oh, it's inverse trig. I was going to say, I don't know what this has to do with solving a triangle, but this has to do with finding the measure of an angle. So sine of this angle is opposite 2 over hypotenuse 30. Now, I could reduce 2/30 to 1/15, but my goal isn't to reduce the fraction. My goal is to take the inverse sine of this value, so it's fine leaving as 2/30. You don't have to reduce to 1/15. But the inverse sine of 2/30 is 3.8. That's the number of degrees. That's not a ratio. So 3.8 degrees is within a 5-degree range. So it is within. We are all good on that problem set. Okay, that's it for the problems for the lecture portion of this. Let's go ahead and start looking at the vocabulary and core concept check before we move on to the official problem set. Number 1, complete the sentence. To solve a right triangle means to find measures of all its sides and angles. When you solve the right triangle, we find all 3 sides, all 3 angles. Number 2, writing. Explain when you can use a trig ratio to find a side length of a right triangle and when you can use the Pythagorean theorem. So trig ratio is when you know an acute angle and a side. Trig ratio, know an acute angle and side. Pythagorean theorem, how do you spell it? Pythagorean theorem is when you know 2 sides of the right triangle. So on these ones, if I knew these 2 right here, I can use that to find the third. If I knew this and this, I could use that to find another side, something like that. That's exactly what they're talking about. And we're going to go ahead and do those problems, however they ask us to do so. So get ready for the problem set officially. Let's look at numbers 3 through 6 together, where we'll determine which of the 2 acute angles has the given trig ratio. Now, I'm going to kind of follow what the book was doing for the lecture portion. They weren't yet using inverse trig. They were instead just kind of taking the setup and asking you which ones happen here. We had questions like this in the last section, and I probably rushed through them more than the book is going to be now. So we want to take the cosine of some angle, an unknown angle, and get 4/5. So I guess the test is take the cosine of A, I'll follow how the book does it. Take the cosine of A, at least to begin with, and the cosine of of C, B is a right angle, and figure out which one is 4/5. Cosine of A is 6 over 10, which is 3/5. Cosine of C is 8 over 10, adjacent of hypotenuse, which is 4/5. So which acute angle? Angle C. Angle C is the one that gives us the 4/5 ratio. So it's all about reducing the fraction. Make sure you know which one's adjacent of hypotenuse. I don't feel like I need to spend like that whole test on it. I'll do it one more time. After that, we'll kind of look at it. I'll still reduce it for you. The sine of the angle is 5/11. It just depends on if they're fractions or if they're decimals, which I wouldn't know the answer to anyway. The sine of an angle is 5/11. So the sine of which angle is 5/11? Let's look at A and C. The sine of A is, well, opposite over hypotenuse. That's 5/11 right there. So angle A. Do I need to test the other one? Only if it was the same, but I could look at it and see. Just for the sake of saying I'd do both of them. The sine of angle C is 4√6 over 11, which can't reduce, but it's also not 5/11. So this one here, this one here. All right. Number 5. Okay, number 5 is an example of where it's a decimal and maybe you don't know your fraction work based off of it, but I know this one, and you probably will know this one in just a second. The sine of which angle is 0.96. Now, you could write it as a fraction. It is, there are a couple ways to do it, but we can use the fractions to get the decimal. So sine's opposite over hypotenuse. Is it going to be 7 over 25 or 24 over 25? It's going to get you 0.96, a number that's really close to 1. It'll be A. 24 over 25, which equals 0.96. So angle A is the one that does that. Again, we are going to, this is kind of just a precursor to finding angle measures on our own. Although they're not asking about the angle measure itself, they're just asking which one gets you the ratio. I guess I understand why they're asking you these, because like I said, it's not about angle measure. It's about understanding how we're really looking into the ratio. and say the sine of which angle gives me that ratio, because that's exactly what we have to do when we find the missing angle measures themselves. The tangent of which angle gives me 1.5. Now 1.5 is also 3/2, or is it, when we do opposite over adjacent, is it going to be 12 over 18 or 18 over 12? 1.5 is more than 1, so we got to divide a bigger number by a smaller number. It's going to be 18 over 12, so that opposite over adjacent should be, boom, boom, for angle C. Tangent of angle C is 18 over 12. And you could go straight to the calculator instead of trying to reduce the fraction. That'll give you the 1.5, so angle C will be that answer there. So I know I didn't test everything. I mean, I did internally, right? Is it 12 over 18 or 18 over 12? It's not going to be 12 over 18. That's less than 1. The exact decimal is the 0.6 repeating, so that's not going to be it. All right, in exercises 7 through 12, let angle D be an acute angle. Use a calculator to approximate the measure of angle D to the nearest tenth of a degree. So this is where we start beginning to use the inverse trig. And I'm going to copy down the problem. However, I'm going to leave some space on these parts, and I'm going to do this probably every time. Well, no, sometimes I won't show this work. I want to begin with it, though. If you want to get D by itself, let's say what you don't do, and I'll tell you this is going to make so much sense. You don't divide both sides by sine. Let's think of two reasons. Let's think of two reasons why we don't divide by sine. Number one, we're not multiplying to begin with. This is not sine times D, despite the fact that I use parentheses here. This does not say sine times D. It is a function. It says sine of D. Much like square root of something. That's a function. Like square root of D equals 0.75. You don't divide both sides by square root, do you? And that's really number two. That doesn't make any sense. Divide by square root? Is square root a number? I guess it's the second root of something, sure, but is that a number? No, it's a function. What the heck does a function? How do you divide a function? Go in your calculator and divide 0.75 by square root. See what happens. Go to your calculator, divide by sine. See what happens. It says, what are you doing? I need a number out. Remember, this is a function, so you don't divide by sine. Anyway, there's an inverse to sine, and it's called inverse sine, but it looks like this. You take the inverse sine of this side and take the inverse sine of that side. The inverse sine of the sine of something effectively, for all intents and purposes, for a right triangle, cancels out those and leaves you just with D. So D is the inverse sine of 0.75. That's an exact answer. Not a very attractive answer, though. We'd rather look at the degree value. So make sure you're in degrees, which I am. I have the inverse sine. I think it would become very apparent if it wasn't. Inverse sine of 0.75, and I'm getting 48.59 or 48.6 degrees. So I'm writing that out. So 48.6 degrees. You probably won't often see me go to the calculator here on out. I'll just type it out and then get it written. Number 8. The sine of D is 0.19. This time I won't leave any space as to know what happens when you do inverse sine here. So D is the inverse sine of 0.19. Remember, 0.19 is a ratio of an, this is what has to do with the previous problems. The sine of an angle is 0.19. That means there's some opposite over hypotenuse that's getting me that ratio. What is the angle that gives us that? That's what we're calculating here. So the inverse sine of 0.19 is around 10.95, so 11.0 degrees. Around 11 degrees. Around 11 degrees. The sine of 11 is around 0.19. That's what we get from it. Number 9 and 10 are cosine. So I'll go back to what I kind of did the first time. I'll give myself some space just to show you it works with all three. The cosine of angle D is 0.33. I must take the inverse cosine of both sides, like so. That's what wipes out the cosine portion on this side, just leaves me with D. And now I'm going to be taking the inverse cosine of 0.33. So let's go to the calculator for that one. Take a look. I'll just reset that each time. Inverse cosine of 0.33. And I'm getting 70.7 degrees about. Fascinating. There's that guy. 70.7 degrees. Number 10. the cosine of D equals 0.64. Let's take the inverse cosine of both sides without actually kind of showing it. So D is the inverse cosine of 0.64. Let me go to my calculator. And I'm getting around 50.2 degrees. Really important that you leave that degree symbol for angle measures, right? These are not radians, so you have to really make sure that you're differentiating between the two. Number 11, the tangent of angle D. Now, this is one of those ones where it's probably easier to talk about what the angle measure would be closer to or bigger than or less than. Oh, let me give myself some room. Tangent of D is 0.28. I know that when I divide opposite by adjacent and it's 1, I'm at a 45-degree angle. But when I divide opposite over adjacent and it's less than 1, I'm looking at a less than 45-degree angle. Take the inverse tangent of both sides, so be gone, and we have D equal to exactly inverse tangent of 0.28 degrees. Again, not a very pleasing answer to us. Let's look at what that'll actually be and how these all work. Inverse tangent. And by the way, how am I hitting this? I'm hitting the second button and then I'm hitting the thing above it. I don't know if I mentioned that, but the function is above these symbols here, and it is for most calculators. So just make sure you're in degrees when you do that. So 0.28, and I'm getting 15.6, around 15.6 degrees, which is clearly less than 45 degrees. So I feel like I did quite all right on that one. And then number 12, the tangent of an angle is 0.72. This should still be less than 45 degrees, but closer to 45 degrees. Tangent of D is 0.72. So D equals the inverse tangent of 0.72, which is, wait for it. Seriously, wait for it. 35.75, so 35.8 degrees. There we go. Okay. That is the first set with those angles there. Numbers 13 through 18, we will solve the right triangle. I'm probably going to be copying and pasting these ones over because I'd like to fill it in as we go. Sometimes some answers depends on the other answers that we have, and sometimes we should know when not to depend on those other answers. So number 13, and I generally like having the visual of a drawing anyway when we do this. Number 13, I have leg lengths of 9 and 12. I'm going to cut right to the chase when it comes to the length of AB, guys. It is 15. The reason I know that is, listen, Pythagorean theorem would get you there. The whole 9 squared plus 12 squared, right? But this is also, and I want to emphasize this, this is a 3, 4, 5 Pythagorean triple, where every value is 3 times larger than it would have been. This is something that, again, over time, you might recognize these, learn these, know how to do those. And I've seen these so many times, I just know that. Tripling 5 gives you 15, therefore AB is 15. Use Pythagorean theorem, you'll still get it. I'll make sure to do it in, I'll make sure to do it in other problems because we're going to have to. Okay, but we still got to find some angle measures, like the measure of angle A. If I want to do that, now 15 is an exact value, so I can, CAN, I can use it in any trig that I like to. For example, if I want to take the sine of angle A, I would get 12 over 15 as my ratio. Now, that means if I take the inverse sine of both sides, I'll be taking the inverse sine of 12 over 15. And again, no need to reduce it or write its decimal form out. If you just type that in exactly, you know to avoid any mistakes. Although that's 0.8, although that's 4/5, you can avoid any mistakes if you just type that in exactly, get the inverse sine, and I just computed it. I got 53.1 degrees. 53, it's approximated, but 53.1 degrees. Now for B, I could also use an inverse sine or an inverse cosine or an inverse tangent, but I also have the 53.1 degrees to work off of. So measure of angle B, this is measure of angle A, by the way, measure of angle B equals 90 minus the 53.1 measure of angle A, which means it's about, I should know that, I just don't want to make a mistake, 36.9 degrees. And I mentioned this in the lecture portion. I talk about not using rounded values to calculate with, but I can use it when adding or subtracting a single rounded value off. However, if it makes you feel any better, I did use the exact value in my calculator and just went ahead and rounded off of that. 90 minus the previous exact answer rounds to 36.9, but it should anyway if you use the rounded value, at least for addition and subtraction of a single rounded value. And that is number 13. We have solved the triangle. We now know all three sides, 9, 12, 15, and all three angles, 36.9, 53.91, and 90. Okay, number 14. You can see why I'm kind of copying and pasting here. I will use the entire thing. You should definitely redraw this if you're writing it, you know what I mean. Get a nice bigger version of it. Not that big. Number 14. This is one where solving that third side should probably require some Pythagorean theorem bits. Even if I reduce these to 4 and 7, as similarity would go, twice the size, that's not a Pythagorean triple. So I might as well just work off this. 8 squared plus 14 squared equals ED squared. So that's 64 and 196, which is 260. So instead of simplifying radicals, I think they're having us round. Yeah, round decimal answers to the nearest tenth. Let's just take the square root of 260 and round that. I guess they're good with it. So, square root of 260 is about 16.1. This isn't degrees, it's just units. 16.1. Now remember, that is approximated. Which means I do not want to use it in my trig function I will use to find the measure of angle E or D. This time, if I wanted to say find E, I should use the 14 and the 8. I'll use tangent, opposite over adjacent. So let's take the tangent of E to get 14 over 18, over 8, excuse me. Therefore, measure of angle E is the inverse tangent of 14 over 8. And I'll let my calculator work that out. It should be more than 45 degrees. So inverse tangent of 14 over 8, I'm getting 60.25, so 60.3 degrees. That is E. The measure of angle D should be 90 minus that. This time I can try and go without the calculator here. That should also technically be approximately equal to 90 minus 60.3, so 29.7 degrees for that one. And again, I could have used the inverse trig stuff, but that should be faster. Go as fast as you think you can. And plus, you're diversifying the problem that way. I know you want to practice trig, but practice everything. Practice everything. Make sure you know everything about your stuff that you can. All right, number 15. There's still 4 more of these to do. Number 15, also not a Pythagorean triple, so if I use Pythagorean theorem, which I intend to, not a Pythagorean triple. There's no fast way around it. Some decimal approximated answer waits in the wings. What is it? We'll find out once we start writing it out. All right, number 15. Let's find the length of YZ. It is one of the legs, so it's going to be on this part of it instead. So YZ squared plus 9 is 81. Excuse me, that's 72. So we'll take the square root of both sides. Now, I would often I'd write 6 root 2 as the answer. This is going to be, but approximated, it's probably going to be around 8.5. Square root of 72. 8.48, so yeah, 8.5, around 8.5 there. So we'll write this, and again, it is rounded, so I don't intend on using it to find the measure of another angle. Let's say I want to find the measure of angle X, and then to get Z, I'll do 90 minus whatever X is. To find the measure of angle X, we should use cosine, because 3 is the adjacent, 9 is the hypotenuse. And I kind of intentionally did that so I can, I've done sine, I've done tangent. Let's go ahead and do cosine. Cosine of this unknown angle X is 3 over 9. Or 1/3, but leave it as 3 over 9. Don't make the mistake in your reduction. So measure of angle X is the inverse cosine of 3/9, or 1/3. And let's see what that approximation is. Inverse cosine of 3 over 9. 70.5. This is degrees. This is an angle measure. The inverse of a ratio is an angle measure. So 70.5 degrees. And then the measure of angle Z should be 90 minus that. Excuse me, and also technically approximated. 19.5. And if you're looking at the scaling, I think that makes sense that those values are what they would be. And again, I never use the 8.5 because it's rounded. I could use exactly root 72, exactly 6 root 2. But just avoid it, right? If you have other options, use them. Please, please, please use them. Number 16. Same as 15. I know a leg and a hypotenuse, and I can use Pythagorean theorem to find the third side as needed. And that's not the order I'm required to find it. If I'm not using that third side in my other answers, in fact, let's do that. If I'm not using the third side in my other answers, maybe I should leave it out of the way and say if rounded values are just going to distract me, let's avoid them. So let's do something like, let's find angle J first, for example. Let's just go back to sine. The sine of angle J is 14 over 16. So J, measure of angle J, will be the inverse sine of 14 over 16. Well, it's just going to be a slightly big angle. So inverse sine of 14 over 16. 61 degrees, 61.0. Of course, they want us to kind of round to the nearest tenth, and this would do that. 61.0. And then G is going to be 90 minus that. Which is 29.0 degrees. All right, so I found those ones first. Now, I want to find HJ, and I'll use Pythagorean theorem for that. I suppose this works twofold, because I said I don't want to be distracted by a rounded value. These are technically rounded values. And I can see why you might go like, well, if I wanted to find this, I could say sine of 29 is x over 16. Yeah, but it's rounded, so be careful. Just go with Pythagorean theorem on this part. I believe it's just best to do. So 14 squared plus hj squared equals 16 squared. Let's make sure we get as exact as possible without making any other mistakes. 196 plus hj squared is 256. Not 266, 256. Subtract 196 from both sides. I think that's 60. So hj is the square root of 60. So that's about, well, 2 root 15. Square root of 60. And normally I was kind of doing that first. 7.7. 7.7 units in length there. And that solves the triangle in whole. Rounded values, but that's what we're going to deal with. Okay. Excuse me, 2 more. Number 17. 17 and 18 this time. We can't really start with Pythagorean theorem. In fact, I'm not going to really use it at all. Because if I did, I only have one of the 3 sides. If I did, that means I'd be using a rounded value or a weird version of an exact answer that involves trig. So let's just kind of let trig guide us this whole way. If I want to find like ML, for example, I'll use cosine because I have the hypotenuse and the angle here is adjacent, or the side's adjacent to this angle 40. So I could say the cosine of 40 degrees is ML over 8, adjacent over hypotenuse. Multiply both sides by 8, you get ML is 8 times the cosine of 40 degrees. Calculator will help you. 8 times the cosine of 40 gives me 6.12, so about 6.1. That's just units. 6.1. Now, KL, again, Pythagorean theorem is possible, but that value is rounded, and I don't want to say 8 times cosine of 40 quantity squared in my Pythagorean theorem, so let's just use trig one more time. Opposite of 40 and hypotenuse with that 8 means I should use sine. The sine of 40 is KL. Probably should have said LM instead of ML. KL over 8. So KL is 8 times the sine of 40. 8 times the sine of 40, which is about 5.14, so around 5.1. So I guess 6.1 squared plus 5.1 squared gets you pretty close to 8 squared. Now, I've almost solved it all. I still need to find this angle right here. That's going to be 90 minus 40. Which is 50. I could have solved that one first, and I think for the next problem I will if it's set up like that. But that solves the triangle. And the last one here among this set, number 18, triangle RST. Ooh, it's big. Triangle RST, and I have the side opposite that 57 there. 18. Whoops. Let's use black. Okay, let's find the measure of angle T first. Y'all, this is going to be 90 minus 57, so that is 33 degrees. Now, I have total amount of choices that I can use to solve any of these things if I wanted to. I could use the 33 or the 57 because I had to find... I'm sorry about the yawning. I'm going to try and just prevent myself from doing it. Because I had to find the 33 anyway, it didn't hurt to do that work to make that happen. Let's just start with the 57, though. I haven't done one of these for tangent for quite a while. Tangent of 57 degrees will get us the length of RS because we get to opposite over adjacent. So that's 15 over RS. And yes, that's a 5, and that's an S. Sorry. Multiply both sides by RS, divide both sides by tangent of 15. They switch places. RS is 15, that's a 5, over tangent of 57. So let's try that. 15 divided by tangent of 57. 9.74, so around 9.7. Should it be less than 15? Yes. It is opposite the 33 degree angle. Let's not use the rounded value, no Pythagorean theorem, but let's find this hypotenuse here. I can either use the 57 with sine or the 33 with cosine. For the sake of diversity, let's use that 33 and let's use cosine. The cosine of 33 is 15 over this RT. So that switch places thing is going to happen. RT is 15 over the cosine of 33. Now, for the sake of if you tried it the other way, if you're checking your work, you're like, wait a minute, I used 57. Okay, if you did, then you'd be doing 15 over the sine of 57. Just so you know, both of these will get you the same answer. I didn't fully set this one up, but I am giving you what you want to calculate. So 15 over the cosine of one or 15 over the cosine of the other will get you what you're looking for. Just to show you, I'm going to do this in the calculator with both. I just did 15 over cosine of 33. Let's do 15 over sine of 57. So either way, you're getting your 17.9 rounded value, which is the last number that we're trying to find there, 17.9. And there it is. Triangle is solved. So we found the different ways that we can solve a triangle. Obviously, there are a lot more problems they could give you, but those are the different setups that can be involved. Okay, number 19. Error analysis. Describe and correct the error in using an inverse trig ratio. The sine of 8 over 15 equals measure of angle t. Well, 8 over 15 compared to t is the opposite over adjacent. We use tangent for that. So we have two options in what to fix here. That would be inverse tangent, or if you wanted to use inverse sine, they should have used opposite over hypotenuse. Their ratio applies to the tangent trig ratio, not sine. If they wanted to use sine, they should have used the hypotenuse in their ratio instead of the adjacent leg. So let's go multiple ways about this. If we wanted to find the measure of angle t, we could have either said that the sine of t, and I like to start with that setup first, decide which one, is 8 over 17. So measure of angle t is inverse sine of 8 over 17. Or we could have said the tangent, instead of sine, of angle t is 8 over 15, like they had as the ratio. So they could have also said the inverse tangent of 8 over 15. Either one or the other will get us the exact same answer. Let's check out the calculator for that. And it looks like they didn't actually continue with the problem, but I want to, just to show you, we get the same thing. So inverse sine of 8 over 17. By the way, this is a Pythagorean triple, not that it matters for us for the problem because we didn't have to find a missing value. Either way, we're getting this 28.1 degree angle measure. So either one works. I don't know which way they wanted us to correct it. but we got the correct value, right, for the measure of the angle. I assume the angle is what we were trying to find, so that's what I put there. Okay, number 20. Problem solving. In order to unload clay easily, the body of a dump truck must be elevated to at least 45 degrees. 20. Whoa. The body of a dump truck that is 14 feet long has been raised 8 feet. Will the clay pour out easily? Explain your reasoning. So my understanding of the drawing is like I have a dump truck here. And then you have this this guy right here. But we're going to raise... No, not the whole thing. Hold on, let me do that again. We're going to raise this part here like that so that it can pour stuff out, right? So we're looking at this being basically our right triangle here. Right triangle like that. And in this right triangle, they said the body that's 14 feet long has been raised 8 feet. So this is the part of the body that they care about, really, to raise the dump truck. Will the clay pour out easily if it's at least 45 degrees? I could tell you the answer without using inverse trig. Oh, by the way, the raising is the angle of elevation. This guy, this is your theta right there, your angle of elevation. So will this angle... Let's change the color. Will this angle here be at least 45 degrees? I could tell you right now the answer is no. This is using what we've talked about by do answers make sense when we talk about, you know, for tangent, opposite over adjacent, all that kind of stuff. Opposite this side is this angle. Opposite this side is this angle. This will have the bigger angle. And if an isosceles right triangle has two 45-degree angles, then this will have less than 45 degrees. So the answer is going to be no, but let's set it up. The tangent of this angle theta, let's figure out the exact value. It's 8 over 14. So theta, the measure of that angle, is going to be the inverse tangent of 8 over 14. And as long as it's less than 45, which it will be, then the answer is no. This won't pour out easily. So when I do that, I am getting 29.7 degrees, which is less than 45. No. 29.7 degrees is less than 45 degrees. That's my reasoning there. That justifies it. All right. Number 21. Problem solving with a diagram. You are standing on a footbridge. It's me. That is 12 feet above a lake. You look down and see a duck in the water. Quack. The duck is 7 feet away from the footbridge. What is the angle of elevation from the duck to you? So they're looking for this right here. Again, if I call that theta, the angle of elevation from the duck to you. It's also your angle of depression from you to the duck. Okay? So in that diagram, it's already drawn there, so I'm not going to redraw it. Once again, it looks like a tangent scenario. Tangent of this angle is 12 over 7. So theta is the inverse tangent of 12 over 7, which will be more than 45. I go back to my reasoning and how I knew the other one would be less than 45. Do I know it exactly? No. That's why I'm using the calculator now. But I should anticipate more than 45, so if I get something less for some weird reason, I know that something went wrong. But this is around 59.7 degrees of the angle of elevation from the duck to you. All right, number 22. How do you see it? These problems tend to go quicker. Write 3 expressions that can be used to approximate the measure of angle A. Which expression would you choose? Explain your choice. Well, the first one is the one that I would use. Given what I already have, measure of angle A, I have the opposite and adjacent, I would use tangent. So I could say the tangent of angle A is 15 over 22. Therefore, the measure of angle A is inverse tangent of 15 over 22. It says expressions that can use to approximate it. This is one of them. I'm not going to actually calculate it for the sake of whatever. Now, what are the other 2 ways you can use it if you don't have any other values? You can still find that third value by using Pythagorean theorem. So with Pythagorean theorem, I could find out that AB squared is 15 squared plus 22 squared. Not a Pythagorean triple, by the way, so I'd have to kind of keep going. So AB squared is... 15 squared. I know 15 squared, but I don't do that plus 22 squared immediately. 709. So AB is the square root of 709. Now, there was rounding that we did before. If I rounded this one, I'd get... 26.6 something, but I don't want to round here. If I wanted to approximate the measure of A, I should use the exact answer if possible. So root 709 will do. So I can say, so there's measure of angle A. Measure of angle A, whoops. I could also, now that I know that that is root 709, now I can use sine and cosine. I'll use sine if I use 15 over root 709. So measure of angle A can also be the inverse sine. Hopefully you understand that setup, 15 over root 709, opposite over hypotenuse. I could use that. And the measure of angle A I could also write as inverse cosine of adjacent over hypotenuse. That's 22 over root 709. Now, none of these values are going to have any rounding error. All of these are exactly the same answer because I did not round root 709. How I wrote it is exactly as is. However, which expression would I choose? Explain my choice. And this problem is taking longer than I said it would, or that I thought it would. I would choose tangent for several reasons. The main culprit is because I already know the opposite and adjacent values. Finding sine and cosine, or using sine and cosine, required finding the third side and using Pythagorean theorem to do so. Plus, and here's the big thing, plus I wouldn't want to make the mistake of using a rounded value in my calculation, which I did not, which means I have to write more to compensate for that. So it's kind of three things there. Using tangent requires less calculation. Using sine and cosine either requires using the exact value, which in some cases can be a big right, root 709 isn't huge, or using a rounded value, which means there's imprecision. So those are kind of the three culprits there. Using tangent for this particular problem was best to find measure of angle A. Now, I never found out the answer. I just know it's less than 45. That's another reason I could use tangent, because I can tell that it should be less than 45. Number 23, modeling with mathematics. This yawning, man. The uniform federal accessibility standards specify that a wheelchair ramp may not have an incline greater than 4.76 degrees. You want to build a ramp with a vertical rise of 8 inches. You want to minimize the horizontal distance taken up by the ramp. Draw a diagram showing the approximate dimensions of your ramp. All right. Let's kind of use more of the line tool this time. So I have a wheelchair ramp. I'm not going to draw a wheelchair. But a wheelchair ramp here. That looks like a pretty hefty incline already. But 4.76 degrees is what I want to diagram there. There's a right angle. But here's the idea of the ramp going up, right? Or going down. That's the ramp itself. Here's the vertical rise of 8 inches. It says you want to minimize the horizontal distance taken up. So this is the distance. This is the unknown. Draw a diagram showing the approximate dimensions of your ramp. Oh, so we still have to solve it all. We still have to find out every little part to this. I thought they just meant set up what you want to find there. So here's the unknown. But I think all dimensions are still needed. So let's just call that X. Let's call this Z. I don't know. Just because. And let's also find this angle measure at the very end. So let's start by finding that X, because that's the whole minimizing thing we wanted to begin with. Sine of 4.76 degrees equals 8 over X. So X is 8 over the sine of 4.76. There's no inverse trig used in finding the length of a side here. So 8 over the sine of 4.76 degrees. That's about 96.406. I'm going to write a few more decimal places to start with to talk about which way I want to kind of write this number. It's probably better to be more precise with that anyway. But regarding X, it says you want to minimize this thing, but you want to make sure that this degree amount is at most 47.6 degrees. If I made X shorter, like 96.4 instead of 96.5, then that incline would be greater. So I need to make sure that this is at least 96.5 96.5 inches. 96.5 inches. What is that? It's like 8 feet? Around 8 feet of ramp. Now Z, let's use the same bit. Cosine of 4.76 is Z. No, excuse me. Let's use tangent. Let's use the 8. Tangent of 4.76 equals 8 over Z. So Z is 8 over the tangent of 4.76. And we'll round up here as well at all costs if need be. So Z is about 8 over tangent of 4.76. It's 0.666. Wait a minute. Oh, 8 divided by. I was going to say something looks way wrong there. It looks devilish. 96.07, so I'll say 96.1. 96.1 inches. The last thing we need is this angle right here. This is going to be 90 minus 4.76. I don't know if we actually need it. They just said the dimensions, so I guess we need all three. 90 minus 4.76. I assume since we have to solve some triangles. 85.24 degrees for that last one. Okay. And that's the diagram kind of solving the entire triangle. I don't know if that's what I needed, but those are the dimensions. All right, number 24. Modeling with mathematics. What did I say this goes to? Let's see. It says on your screen. 32. Oh, 32. I thought it was 28 or something like that. Boo hiss. Modeling with mathematics. The horizontal part of a step. Let me yawn a little bit. Give it a second. Okay, I'm back. It's incredibly rude for me to yawn during something that's self-proclaimed as brand new and exciting. Tired is tired. The horizontal part of a step is called the tread. So there's a diagram for us. The vertical part is called the riser. The recommended riser to tread ratio is 7 inches to 11 inches. I like these kinds of things because they're like, is that real? I guess maybe, yeah. So, tread riser, recommended 7 to 11. And I'm guessing it's better to make that bigger than that in general. But 7 to 11 inches. Okay. Find the value of X for stairs built. Find the value of X for stairs built using the recommended riser to tread ratio. Find the value of X for stairs built. Oh, I didn't see where X was. I was so lost. Okay. I was like, what's going on? So, okay, if this is the 7 to 11, that means this can apply over here. So let me redraw what they have instead. Maybe we get to use the other one, but instead it's more like use this right triangle, and then the riser part can also apply here. So this can be the 7, and the tread can apply here. This can be the 11. So here's the X. I was like, what do they want? So the tangent of X is 7 over 11. So X is the inverse tangent. X degrees is the inverse tangent of 7 over 11. So, less than 45. 32.47. So 32.5. 32.5 degrees. That's part A. Part B, you want to build stairs that are less steep than the stairs in part A. That's kind of what I was saying. Give an example of a riser to tread ratio you could use. Find the value of X for your stairs. Well, you could use 6 to 11. You could use 6 inches to 11 inches because that'll lower the rise while the tread stays the same. So let's do that same thing. Let's use the new X, or the inverse tangent of 6 over 11. So now this will be, and I could use 7 over 12, something like that. But 6 over 11, inverse tangent of that, it's going to give me an angle this time of 28.6 degrees. Not much less, but a little less. Not the recommended, though. Not the recommended. All right. Number 25, using tools. Find the measure of angle R without using a protractor. Justify your technique. What? Oh, okay. Okay, I guess I can use a ruler. So a protractor, if you guys know, a protractor is what can use to find exact angles of something. You can like line it up here and say, oh, look, that's a 28-degree angle. No. Okay. Instead, let's use like a ruler. Let me keep it bigger for now so I have more rounding error. I have better error with my ruler now. It doesn't matter what the size actually is. Yours is going to be different than mine. It depends on what you're looking at, how you're looking at it. If you divide it, you can follow along. Maybe you don't have this problem at all, and I'm just talking to myself. But I'm going to measure what 2 of these 3 side lengths are, and I'll just go ahead and find these ones here. So when I enlarge this to this amount, this is about 7.5 centimeters. Just based on the ruler bit. That's about 7.5. And then let's find which one I can be more precise with. The hypotenuse or the... That's not bad. It's about 12.5. Let's just use that. 12.5 centimeters. I just need 2 of the 3. And without using a protractor, I can find these angle measures still by using trig. So, find the measure of angle R. I didn't know which one to find. Find the measure of angle R without it. I can use sine. The sine of angle R is around 7.5 over 12.5. And assuming that my computer enlarged or reduced this all to scale similarly, then the answer should be what they would expect you to get. So we're going to get the inverse sine of 7.5 over 12.5. Should be about, within a couple of degrees if there's an issue. But 7.5. Again, I used a ruler for these things here. It doesn't matter if this was centimeters, inches, whatever. The whole point is all these triangles are similar. 36.869, so around 36.9 degrees. So if it's anywhere close to 37, then I did something right? Okay, number 26. So we go to 32, right? Your friend claims no. Inverse tangent is not 1 over... Okay. Your friend claims inverse tangent of x is the same as 1 over tangent of x. Is your friend correct? Explain your reasoning. Oh, boy. Okay. Your friend is not correct. Your friend is not correct. And I'm not blaming your friend. I'm saying this is a common mistake. And it's not your fault either. It's not your friend's fault. My friend. I don't know if I used to say my. I've said it the last 2 times. My friend is not correct. The notation for inverse tangent may mislead one to believe it is the same as raising tangent to the negative first power, when really it is simply a way of saying inverse tangent. Let me say this. The notation, not for, but the notation like that. Boom. It's really a way of saying inverse tangent. When you taking x means finding the angle of the measure of an angle whose opposite over adjacent ratio is x. Whereas taking 1 over the tangent of x means, you won't know what this means literally, means taking the cotangent of an angle measure x, which is not the same thing. Case in point, let's try it with 2 numbers. Let's use 30. If I take the inverse tangent of 30, remember that's not a degree measure, that is a ratio. That's 30 over 1. That's the same as finding the angle measure here, theta, of a right triangle who has a 30-to-1 opposite to adjacent ratio. This number will be very, very close to 90. The inverse tangent of 30 is 88.09. It's around 88.0 degrees. Remember, the inverse tangent of something is a ratio. This is an example, by the way. Inverse tangent of a ratio, is an angle measure. Whereas if I did 1 over the tangent of 30, this 30 is 30 degrees. Taking this one will be the reciprocal of taking the tangent of 30, which is called taking the cotangent of 30, by the way, which instead of doing opposite over adjacent, I'm doing adjacent over opposite. Tangent of 30 is 1 over root 3. Tangent of 30 is root 3 over 1. You know what root 3 is about? I forget, 1.7 something. So what is 1 over tangent of 30? 1.732. So it's the same as the square root of 3. 1.732, which is equal to the square root of 3. Not the same. Not the same. So, no, taking inverse tangent, tan negative 1, right? That's not something you want to say. Tan minus 1. It's not what it means. It's a way of saying inverse tangent. This is a way of saying cotangent. No, totally not the same. Okay, good thing that they have. But no, your friend is mistaken. Using structure in exercises 27 and 28, solve each triangle. Okay, they want us to explore a little bit here. Let's find stuff. Let's have this kind of just copied and pasted. I don't know what to do yet. I haven't really looked at it. All right, triangle JKM and triangle LKM. Let's start by finding values within JKM. I think I just have more information here as an overall. I can find this side length and this side. Well, let's start with this. I can find this angle measure. That's 49 degrees, right? These add to 90. This is a right angle, by the way. Let's use the 41 to find these other things, though. Let's take KM, the inverse, excuse me, not the inverse sine. Sine of 41 is, oh, not sine. Tangent. Tangent of 41 is KM over 9. So KM is 9 times the tangent of 41 degrees. I'm going to leave that exactly like that for now, though. You know, I've mentioned not to round things early. This time I might have to use this exact answer because this is now a value in this triangle that I can use. Let's leave it like that for now until we have to do something later. And this is probably one of the parts where the book might do early rounding or you might do early rounding. I'm going to encourage you not to. If I want to give you the rounded, sure, I'll just still have it, but I'm not going to be using it. It's around 7.8, but it's 7.82358.064, etc. So it's around 7.8. We'll save that for later. We'll have that as the answer officially, but this is what I need to use to calculate other things. Now, I could cosine of 41 is 9 over JK. And swap places with cosine of 41 degrees here. JK is 9 over cosine of 41, which is about, and this one I'm fine approximating with because I don't think I'm going to use this again. 9 times cosine of 41, divided by cosine of 41. 11.9 feet. I didn't realize these are all in feet. Feet. 11.9 feet. Okay, I'm going to use that 9 times tangent of 41 degrees to find some things out. And this is just unfortunate because you're going to see a lot of, instead of me using 7.8, I'm going to use this exact thing. It's going to be kind of funky because we need to find 3 things still. We need to find this missing side and we need to find 2 angle measures. Let's start by the missing side, ML. This guy. All right, ML squared plus, this is the non-fun part, 9 times tangent of 41 squared equals 21 squared. So this is 81 times tangent squared of 41. I'm still writing exact. I'm not going to round early. And this is 441 if I know my perfect squares here. So ML is 441 minus 81 times the tangent squared. Sorry, that's squared. Squared of 41. So if we take the square root of both sides here, ML will be, this time I can approximate because I don't plan on using this later. So let's go to the calculator. Let's go to the calculator and I'm going to do square root of 441 minus 81. This is 81 times, in parentheses, tangent of 41, close parentheses, squared, and close parentheses for the end of the square root. So kind of weird stuff, but that's all that's written inside there, and it's around 19.5. Now I wanted to make sure to not round anything early. I did not. I feel much better about my answer. I don't want to make a mistake and have it be 19.4 or 19.6, and I know that that sounds a little snobbish to just be that close to having a different answer, but use exact values when it involves some of this other stuff. Squaring, square roots, all that stuff. Okay, not lastly, I still have two more things, but last time I have to use this 9 times tangent, etc. Let's do inverse trig on K or L. Let's not use the 19.5. Let's use this one with 21. Let's use, say, cosine to find angle K right here. I have some room up here to do so. So cosine of angle K, this is just one of two problems, is 9 times tangent of 41 divided by 21. So K is the inverse cosine of 9 times tangent of 41 over 21. So there's a tangent inside of an inverse cosine. Let me type that out. Inverse cosine of 9 times tangent of 41, close that one parenthesis, divided by 21. And I'm getting 68.12. So K is about 68.1 degrees. Is it completely harmful to have just an approximated answer to the nearest decimal place? No. Am I intending to precision that way, though? No. So I'm going to use that. So 68.1 degrees. Now I'm going to use this rounded value, 68.1, to get this guy. 90 minus 68.1. I don't want to get that wrong, so let's see. 90 minus, I think it's 21.9? 21.9. 21.9 degrees. Okay, so I've kind of answered everything there now, and I'm now going to erase this and change it to what it was. I hope that this made sense. That's 7.8 feet. So I have everything in terms of feet and degrees there. 9 feet, 7.8 feet, 11.9 feet, 19.5 feet, 21 feet. 41 degrees, 49 degrees, 68.1 degrees, 21.9 degrees, 90 degrees, and 90 degrees. We have solved both triangles. The only part that's kind of pushy on that, of course, is me using an exact value instead of a rounded value. Would have we gotten the same answer using rounded? Maybe. Would have it, if it was wrong, would have it been off by maybe just 1/10? 1 decimal place, a little thing? Maybe. Do I feel right in getting exact answers? Absolutely. Number 28. Triangle TUS and triangle VTW. Let's solve them. I'll leave it over here this time. Feels better. All right. I want to use this UT at TUS triangle first. I have the 4 and the 64. This is partial here, and I don't have any angle measures. So let's find this angle here to start with. This guy is 26 degrees, being 90 minus 64. This length will not be used in the future. Let's just go ahead and get it out of the way now by using tangent with 64. So tangent of 64 degrees is this length of TU over 4 meters. So TU is 4 times the tangent of 64 degrees. Again, I'll just round this to the nearest tenth now. I won't be using it later. 4 times tangent of 64 is 8.2 about. 8.2 meters. Okay. Now let's find this hypotenuse ST. The unfortunate part about this, of course, is it'll be rounded, and I'm going to be using that rounded value to find other things. So, boy. All right. So let's use the 26. That's exact. Let's use sine. Sine of 26 is opposite 4 over hypotenuse, this ST. And that's a 4, not a U. So 4 over ST. So ST is 4 over the sine of 26. Now, this is an exact answer. It's the one that I really prefer to be keeping right now. So keep this in mind. This is 4 over sine of 26. This will be used in all my problems that I do with the plus 5. Oh, that's not going to be fun. I might use the rounded. I might use a more... How about this? I'm going to write the rounded value there, but in my calculator, I'm going to use the exact value. Does that make sense? 4 over sine of 26. So it rounds to 9.12468. I'm going to say 9.1. 9.1 meters. But here's what I'm going to do in my calculator. I'm going to always be using that exact answer in some way. So I have this 9.1, and I never use this just alone. This plus 5 gives me the entire length from V to T. That's exact. No rounded 14.1. If I want to use this, I have a storage variable. I can also recall previous answer, but sometimes I'll get different answers. So I can store this variable into something. It says from v to t. Let's just call it x. I don't see. Is this x? I'm going to store it as x. So anytime I use x, it's going to be the exact number. I'm going to write 14.1 on this screen. I hope you don't mind. 9.1 meters. So that solves this one triangle. VT is about 5 plus 9.1, which is about 14.1, also equals x. Okay, I'm going to have that in my calculator there. So 14.1 meters is this whole hypotenuse right there, 14.1. That's important because 9 is another leg that I have on this thing. I'm always going to use the exact version of the 14.1 to find things though. So if I want to find the length of TW squared plus 9 squared equals my 14.1 squared. Again, that is a rounded value. I'll be using the exact in my calculator. TW squared is, well, I'm going to subtract my 9 squared. Let's see. My exact answer squared is 199.5, rounded, is 199.5 minus 81. So this is the square root of whatever this thing is here. And again, in my calculator, I'm doing this exact answer stuff. So minus 81 and taking the square root of that. So of the 118.5 value, which is about, and I know I'm being a little picky. Problem when dealing with me, 10.88 is around 10.9. And I don't doubt you'd probably get the same answer using the rounded values. I just want to be sure. So 10.9 meters for TW. So I'm getting this guy here, 10.9, 10.9. The last things to find are the angles, and I should probably still be using that exact one here because this is rounded. I still have it as the rounded, but I'm going to use that 14.1 because I know I can recall it as x. So if I want to find this angle T, and it's not actually technically T, right? It's a bigger angle thing at large, but in this one triangle. So T, sine of T is 9 over my 14.1. Opposite over hypotenuse. So T, inside the big triangle, is inverse sine of 9 over 14.1. So in my calculator, I'm going to be doing this. I'm going to take the inverse sine of 9 divided by, now my 14.1 value I have stored as x, like that, instead of actually writing 14.1. I get around 39.6 degrees. So 39.6, there, 39.6, and I wrote it up here. The last one, angle V, should be 90 minus 39.6. Which is about 50.4 degrees. Okay. All right, I believe that solves those two triangles in full. Remember, VT was all of 14.1 rounded. Okay, was that the second one? Yes. Number 29. Mathematical connections. Write an expression. This looks like graph stuff. Hold on. 29. Write an expression that can be used to find the measure of the acute angle formed by each line in the x-axis. Then approximate the angle measured to the nearest tenth of a degree. Let's put this on a graph and see what we're dealing with here. So the x-axis is this guy. Keep that in mind. Here's y equals 3x. Now, I've mentioned before that finding angles from slopes isn't an ideal task. However, if you use inverse trig, it's fine-ish. You still got to deal with lengths when you can, so we might have to do that. I actually don't yet know on this problem. Let's find out. I'm going to draw everything in like blue. So here's this line. This will be y equals 3x. Let's do y equals 4/3 x plus 4. So rise 1, 2, 3, 4, 1, 2, 3, and 1, 2, 3, 4, 1, 2, 3. Okay, so with the x-axis, I really just need this triangle. 1 second. I guess I don't need them to go this far. I care most about actually just this part here. Well, I don't really know. Oh, these are two different problems. Each line of the x-axis. Okay, these are two different problems. I'm sorry. I don't need this one yet. I don't need it. I don't need it. If you don't mind, I'm going to leave that out for now, though. So what does this one make with the x-axis is the question. Just ignore that point. It's all similar triangles from here, right? So if I could draw a line from here, for example, to deal with this. It depends on how you want to do it. You can make it smaller or bigger. But this is a length of 1, 2, 3, and 1, 2, all the way up to 9, right? 3 and 9, right angle. So what does this thing make with the x-axis? We want to find out what this angle is right here. If I call it theta, I can use tangent. Tangent, this is part A. Tangent of theta is 9 over 3, so which is 3. Theta is the inverse tangent of 3. So what's the inverse tangent of 3? Well, 71.6 degrees about. Approximate the thing to the nearest tenth. Okay, so that's what we did for part A. Part B, hope you don't mind me just kind of changing this. Normally I'd leave all the record, but you can go and rewind it if you need to. So I'm going to go and do this. Boom. I need to hit this point now. So part B, let's do that again. And because it hits this one point here, we can do another count, probably using tangent, seems best. So part B, we have a length of 1, 2, 3, 4, 5, 6. Wait, 1, 2. And a length of 1, 2, 3, 4, 5, 6, 7, 8. This is a 3, 4, 5 triangle. If this would be 6, 8, and 10. And I think I forgot if we said what kind of angle that was. So here we go. This time theta is going to be the inverse tangent of 8 over 6 on this guy. So inverse tangent of 8 over 6. Get about 53.13 degrees, 53.1. Okay, those are just the visuals of that. Clearly, you'd probably draw it 2 separate times for that to happen, but there it is. Okay, number 30. Thought-provoking. Simplify each expression, justify your answer. Well, see, the book never called this out. I already did. So the inverse sine of the sine of an angle is just the angle itself. This is part A. I dare not justify these things. These are the exact, I mean, I'll talk about them out loud. Well, I guess if I talk about them out loud, then I can write it, but I'm not going to mathematically justify it. The tangent of the inverse tangent of a ratio is just that ratio. And the cosine of the inverse cosine of a ratio is just that ratio. Now, what I want to call out here, I said them out loud, this is an angle. These are ratios because of the actual setup of what they were before. So as far as justifying the whole set, if I take the sine of an angle, my result is a ratio. If I take the inverse sine of that ratio, I get an angle in return, the original angle in return. That's for part A. Part B, if I take the inverse tangent, cosine of a ratio, I get an angle. If I take the tangent cosine of that angle, I get my original ratio in return. So that's what's happening there. That's why those things cancel when you do those. There are exceptions to things that are more than 90 degrees. Because when you take the inverse sine or cosine or tangent of something, you'll either get something negative between negative 90 and 90 for sine and tangent, and you'll get something between 0 and 180 for cosine. Not going to explain those. Those are saved for IM3 and pre-calc. But the point is, you won't always get the same thing back, but you'll get the reference angle back when you do those. Okay, number 31. Reasoning. Explain why the expression... Okay, so this was one I wanted to actually bring up in 9.5, but now I see what's popping up. Explain why the expression inverse sine of 1.2 does not make sense. This is a really good question. let's go to the graphing calculator and try that. Inverse sine of 1.2. Error domain. Why doesn't this work? I want you to imagine where this would exist. So inverse sine of 1.2. Whoops. Inverse sine of 1.2 also means something like, remember, 1.2 is a ratio. Let's say it was 1.2 over 1. Sine is opposite over hypotenuse, right? SOHCAHTOA. So imagine, how can I have 1.2 over 1 not possible in a right triangle? Not possible for hypotenuse to be less than opposite side. This is why this isn't possible. There's no right triangle that exists where you can have the hypotenuse shorter or equal to, not really possible, but we still use it. Can't be less than the opposite side, and that's what we're talking about if this was our angle there. So there's no angle for which this exists. That's the reason. That's the reason. And the last question, number 32, using structure, the perimeter of rectangle ABC. Oh, I thought we were talking about triangles. The perimeter of rectangle ABCD is 16 centimeters. Let's bring it. P equals 16 centimeters. And the ratio of its width to its length is 1 to 3. So if its length is, the width is 1 to 3. Segment BD divides, ABCD. BCD. Segment BD divides the rectangle into two congruent triangles. True. True about rectangles. Let's try that again. Two congruent triangles. Find the lengths and angle measures of these two triangles. Well, they will be congruent. So if I find it for one, I'll find it for the other as well. So let's first find out what let's find out what these x values are and such. So 3x, two 3x's plus 2x's is 16. That's 6x plus 2x is 16. 8x is 16, so x is 2. So this is 2 centimeters. This is 6 centimeters. I could have used x for ratios to find angle measures, but I need to find out the side lengths of the triangles, which means I need to find BD as well. So BD squared is 6 squared plus 2 squared. 36 plus 4, which is 40. So BD is the square root of 40. Now, as a simplified radical, would be 2 root 10. As a rounded value, it's probably around 6.5. Square root of 40, 6.324, it's around 6.3 centimeters? Centimeters. 6.3 centimeters. Now that's rounded. Let's find out the length of, say, this angle here and this angle here. Let's just find one of them. Let's call it angle D. I'm not really concerned about which part of the triangle it's in because the two triangles are the same, right? So angle D, I'll just call it the same. Let's use tangent. Tangent. Didn't we use inverse tangent of this already? Tangent of angle CDB equals 6 over 2, which by the way is 3. So measure of angle CDB is inverse tangent of 3. I calculated this just a second ago. Inverse tangent of 3 is 71.6. Cool. They didn't think I was going to remember that, did they? 71.6 degrees, which also means, by the way, this is 71.6 degrees, and also this is 2, and this is 6. So B is 90 minus 71.6 degrees, which is 18.4 degrees about. So that's the two triangle parts. Hopefully me filling that out made sense. You can find ways to write it that's not as sloppy as that, but that's what we use to get all that. And that is the last problem. All right, guys, that'll do it for this one. This is Mr. Robinson. Thank you so much for watching. Cracked it in under 90 minutes time before the end of the softball game was over. And that is the end of the chapter. So as I said, this really was a good review for everything in chapter 9. Didn't really do a lot of 45, 45, 90, 30, 60, 90s. Hit a couple Pythagorean triples that weren't a massive use. So it was a lot of trig, but Pythagorean theorem was also hit. A big part of just a squared plus b squared is c squared. It was probably more 9, 4, 9, 5. And we added some more in finding angles, and I'm glad they had it here. I get why they separated the sections. Otherwise, they'd make like a 200 problem set for all of them. But the order isn't also a requisite when it comes to learning it. It's just a way that every question flowed. So I hope that all connected for you. Next, coming up for this video series when it comes to things is the Chapter 9 review out of the textbook, the Chapter 9 test and cumulative assessment of the textbook, and at some point within all that is going to be my Are You Ready packet, assuming my colleague makes one for me. Again, you'll find that on this channel in this playlist here. So thank you guys so much for watching. Take care. I'll see you in the next one.